everyone, in this video let's study the forward converter together. So the forward converter is derived from buck converter. This makes these two converters very similar. So in this video I will also, like the flyback converter, point out the difference between buck converter and the forward converter. So if you have a good understanding of buck converter, it will be really easy for you to learn the forward converter. First, let's still plot the on-state and off-state of the forward converter. So this is our on-state and off-state of our forward converter. It looks complex, but actually our secondary part, this whole part, is exactly same as buck converter. So this part follows same principle of buck converter. The second thing I need to point out is we have two inductor here. This inductor and this inductor. This inductor is a real inductor. But this inductor is actually the magnetism inductance of transformer. We just split that from the transformer for our analysis. Let's look at our inductor. And when we look at our inductor, we need analyze both inductor. So let's first have a look of our Lm. So let's plot the Lm waveform together. For the Lm, when the converter works in on states, the voltage is V in, and off states, the voltage is still V in. To make sure our energy not accumulate on our Lm cycle by cycle, there's two very important things in forward converter. The first thing is our Lm always work in DCM. This ensures the energy stored in Lm always cling to zero by the end of each cycle. And the second thing is the duty cannot be larger than 50%. So this is two very important things in forward converter, and you should always remember it. So because Lm is always working DCM, for our delta ILM, we can always use the on-state to calculate, which is T on times V in divided on Lm. Okay, this is all we want to know from analyzing Lm. Let's analyze L together. So L is in our secondary side, and as I just said, it follows the same principle of buck converter. So this is very easy. Let's first plot the voltage waveform and current waveform together. So when it's on the on state, our voltage on the inductor is N times V in minus V out, and at the off state, it's minus V out. And we do the same thing as in our buck converter, so that we can have our delta IL, where it's in the on state is NV in minus V out divided on L times dt, and at the off state is V out divided on L times 1 minus dt. So on-state delta IL should be same with our off-state delta IL. We know our V out divided on V in equals to N times D. Difference from our buck converter is we times winding turns here. The second thing is we can know our delta IL. We can use both our on-state to calculate the delta IL, also the off-state to calculate our delta IL. And our average IL is also same as our buck converter. So our average IL is equal to V out divided on R. When we do the analysis to the capacitor, as I said, the secondary part is always follows the same principle of buck converter. So this is also same as buck converter. Our delta V out equals to 1 minus D times V out divided on 8LC frequency square. After we analyze the CCM mode, let's move into our DCM mode. For all the converters, the boundary happened when average inductor current is half of the delta IL. First thing we want to know is our voltage conversion ratio. I'll directly give you the duty of forward converter when it's in DCM is equal to square root of 2LVL square divided on T times N square V in square R minus MV in R V out. Why I give you this long equation is, let's recall buck converter when it's in DCM, the duty equals to 2LVL square divided on T times V in square R minus V in R V out. You can see that the only difference between this equation is I replace the V in buck converter to MV in, and we got this equation. The second thing we want to know is we want to know the critical resistance. The critical resistance is exactly same as buck converter. We use 2V out divided on delta IL to calculate the critical resistance. So in forward converter, what we should remember is the voltage conversion ratio in CCM, how to calculate delta IL in CCM, the average inductor current, delta V out, or same as buck converter, the voltage conversion ratio. Only remember to replace your V in buck converter to MV in, you get the forward converter formula. And the critical resistance is exactly same as buck converter. And the most important thing is always remember in forward converter, LM is always working DCM, and our duty cannot be larger than 50%. Okay, let's do this forward converter problem together. In this question, our input is 30 volts and our output is 380 volts. Our frequency is 100 kilohertz. The first question asks us to design the winding turns of transformer. So because our duty cannot be higher than 50%, so we use 50% as our limit to calculate the turns. We first calculate 380 divided on 30 times 1 to is equals 25.3. So we need to pick a value that's larger than this one to make sure our duty is smaller than 50%. So I pick n equals to 30. You can pick your value. And the second question is to calculate the duty when the converter works in CCM. Our duty equals to V out divided on MV in, and here is 42%. And the on state and off state time is T on equals to 4.2 microsecond, and T off is 55.8 microsecond. The third question asks us to calculate the delta IL of LM, and as our LM is always work in DCM, so we can only use on state to calculate the delta ILM's value, and I got 4.2 M here. The fourth question is when the peak-to-peak value of inductor current ripple should be lower than 0.3 M, compute the inductance of L. We use here I choose the off state to calculate the L. You can use the on state formula. It should give you the exactly same number. And my result here is 7.35 millihenry. Alright, the last question is when the peak-to-peak value of output voltage ripple is 1 volt, compute the capacitance at the output side. The capacitance is equals to 1 minus D times V out divided on A delta V out L frequency square is equals to 375 nanofarads. This is all about this video. We will see you in next video.